Art Lerner-Lam. I'm a seismologist at the Lamont-Doherty Earth Observatory of Columbia University. I'm also Associate Director for the Division of Seismology, Geology and Tectonic Physics. Well, seismology is the study of earthquakes and the Earth. There are two parts of seismology. One is to actually look in detail at the earthquakes themselves, and the other is to use the earthquakes as a sort of light source for photographing or imaging the Earth. Imaging the Earth is something that we sometimes call structural seismology, but very much like a CAT scan you might get in a medical office, we use the waves generated by earthquakes to illuminate this internal structure of the Earth. One of the great mysteries of the planet is, what is the Earth made out of? How does that stuff move? And seismology is really a remote sensing tool for us to try to understand that. Well, one of the wonderful things that has happened in the earth sciences over the last 40 years is what we call the theory of plate tectonics. And plate tectonics really is a very descriptive working hypothesis that allows us to take diverse sets of observations and put them together and see if we can understand how the planet as a whole works. But plate tectonics really is just a kinematic theory. What that means is that it really only describes the motions of the plates, how fast they move, what their boundaries look like, and so on. But we really don't know how they move or what forces them to move. And to do that, we really have to penetrate into the interior of the Earth. Now, in many ways, the Earth is like a big bubbling pot of thick soup. And on geologic time, the Earth is really a fluid. And of course, on human time, it's a rock. You hit a rock with a hammer, it might crumble and break. But on geologic time, the Earth really behaves like a big melted plastic ball. And it's the movement of that molten material, that plastic, that warm plastic material that really drives the plates. But we can't observe it directly. And so we use earthquakes and what we call structural seismology to image it. If you were taking, or if you were interested in the workings of the human body, what you would do would be to take CAT scans or three-dimensional images from time to time to time to get sort of a movie of how the body works. Well, that's exactly what we're doing with seismology. We take CAT scans from time to time, and it gives us some indication of what's going on. Of course, we can't do our experiments in geologic time. It would just take too long. So we use proxies to let us attain kind of a movie representation. It's something that we sometimes call 4D seismology. Well, 4D seismology really means that we're looking at the Earth in three dimensions, up, down, north, south, east, west, the three physical dimensions of our real world, and sort of getting a time history. Geologic time occurs over millions of years, so we, in the lifetime of a single scientist, you can't observe that. But over the years, we've developed proxies to replace that, and we can use seismology, we can use petrology, the study of rocks, we can look at the ages of rocks in various ways, we can even use paleontology, the study of fossils, to get some indication of what the history of the Earth looks like. But the real incredible thing that has happened is that the three-dimensional aspect of that problem has really just exploded in the last decade or so. Seismic instrumentation used to be pen and paper. Used to have these rotating drums with a pen that would wiggle every time an earthquake wave passed, for example. But right now, of course, we record that digitally. That's like the move from analog tape to CDs or DVDs. So that's one element. But the other is that, we used to have to wait for an earthquake, and we didn't have very many instruments in the ground, just a couple of hundred. But now we can put thousands of instruments into the ground, and so we get a much finer picture, a much more highly resolved picture. It's like as if we had been shooting through cheesecloth or gauze or Vaseline or something like that. We've never been able to really see the Earth in all its clarity, and now we can. We're part of a project called EarthScope, for example, which is like a giant high-resolution telescope, not pointed to the universe, but pointed down into the Earth. We know less about the Earth, really, than we know about the universe at this point. But this telescope is just giving us fantastic images. We're starting off with the North American continent, and our hope is that over the next decades we'll be doing that around the Earth as well. Well, earthquakes are a weird kind of phenomenon in the following sense. When we talk about the theory of plate tectonics, the working hypothesis is that it's a smooth motion of the plates, that the plates move over geologic time with predictable rates. It's as if they're kind of a slow movement of traffic, if you will. Everybody's sort of moving at a rate that stays constant in time. But obviously earthquakes happen. Earthquakes predominantly occur where the plates interact with one another along what we call plate boundaries, obviously. Sometimes those plate boundaries are sideways, like we have in the San Andreas Fault or in the earthquake that happened in Haiti. Sometimes those boundaries are compressional, like what happened in Chile or what might happen off the coast of Seattle. And sometimes those boundaries are what we call extensional. Best example of this would be the Basin and Range in the western United States around the longitude of Salt Lake City going all the way west to the Sierra. So those three type of boundaries sort of describe how the plates interact. But earthquakes, of course, are not a continuous process by any means. They're really what we call a stick-slip process. So while the hypothesis of plate tectonics, or the working model, is that the plates move at a relatively constant rate, at the boundaries they stick and they slip. The boundaries don't move at a relatively constant rate. Instead, the boundaries stick, and when they stick, the movement of the plates stresses that boundary, and eventually that stress overcomes the strength of that boundary, and it breaks. And that breakage is an earthquake. That's sort of what we call the stick-slip model, or we have other names for it, but that's basically what happens. The problem that we face as earthquake seismologists is that sticking and slipping is almost a chaotic process. Not quite, but almost. And so it's very difficult to predict on a day-to-day basis. Over geologic time, of course, it's very predictable. We can get an idea of where the active plate boundaries are. Those plate boundaries, of course, are major faults in the Earth. And we know where the earthquakes will occur. But because we can't predict the stick and slip cycle very well, certainly over human timescales, we can't really get what we call a prediction. But there's a deeper understanding of it that allows us to forecast instead of predict. And by forecast, I mean, well, first of all, we know where they occur because we know where the plate boundaries are. But we can get a sense of what the probability of an earthquake might be in two ways. One, by looking at the past history, and if we have enough earthquakes, we can sort of get a statistical model of when earthquakes might occur. And that gives us some probability. And the other is to actually do a bit of forward modeling and actually take the plate motions, take a model of the friction along the plate boundary, take a model of how the stress builds up, and sort of predict when and where, or I should say forecast when the next earthquake might occur. And it's gotten to the point where we can probably do that over the span of a decade or two, perhaps 30 years, to the extent that we can sort of provide an actuarial table. If you wanted to go out and buy insurance in California, as a matter of fact, there is such an actuarial table to help you determine what your rates are, or I should say help the insurance companies determine what they're going to charge you. Of course, we didn't have that for Haiti. We had barely had that for Chile. But the point is we're getting better at it. So, you know, one of the exciting parts of earthquake seismology is that the better we get at forecasting earthquakes, the closer we might actually come to a prediction that is useful on human time scales. Well, they're unusual in the sense that statistically it's unusual. You could say it's a statistical anomaly, statistical fluke. There's no reason to think that earthquakes are occurring any more frequently now than they occurred last year or 10 years ago or 10 years into the future. There's no reason to believe that. And it has nothing to do with global warming. Believe me, that's a question that we often get. One of the things we learn as seismologists is that earthquakes can occur at any time and any place. In fact, they don't even have to occur at plate boundaries for that matter, but that's a whole other topic. But along some of the major plate boundaries, like the Pacific Northwest, we have evidence of past earthquakes. And that actually is an interesting thing. Obviously, we didn't have instruments going back more than about 100 years or so, so we don't have an instrumental record. But we have a record from old newspapers, for example. We have a record from some old mission records, particularly in California, Spanish mission records, and elsewhere throughout the Western Hemisphere. We have very long historical records in China and Japan and in parts of Asia where people have been writing things down for quite a few centuries. But in some places, we simply don't have that written record, and we have to rely, again, on proxies. There are a couple of things we can do in a place like California or Seattle. Let's take California first. One thing we can do when we have a fault like the San Andreas is to actually dig a trench across that fault. And when we trench across faults like that, and you do that trenching at different places, you can actually see in the disturbed soil the record of past earthquakes. They may occur every 150 or 200 or 300 or 400 years, but with very good carbon dating or other geological techniques, we can get a good sense of what that history is. And by doing that trenching at various places along the fault, we can even get an estimate of the size of the rupture, which gives us a way to calculate the magnitude. That then allows us to calculate the repeat interval, say, for these very large earthquakes. In Seattle, or I should say more generally off the coast of British Columbia, Washington, and Oregon, going down into Northern California, that's a different kind of a plate boundary. It's what we call a subduction zone. It's a convergent boundary. It creates the cascades and the volcanoes, so we can't trench it. But what we can do is look at the history of uplift on the coast, because every time an earthquake occurs, the upper plate, which is basically the coast of Washington and Oregon and Northern California, gets bumped up a little bit. And by looking at the sedimentary record, actually sometimes it can go down as well, but looking at the sedimentary record, looking at the way, say, even trees are drowned by encroaching water or lifted above the water table or so on, you can get a sense of the history. People who look at things like tree rings or the history of corals, there aren't any corals up there now, but if we go elsewhere around the world, we see that. These are all proxies for past big earthquakes. There's another proxy, which in particular for the Pacific Northwest works, and that is earthquakes along that boundary have a tendency to generate a tsunami. And when a tsunami propagates or moves across the Pacific Ocean, particularly a big one, when it hits islands on the other side of the Pacific, you get what's called tsunami deposits. It's a very turbulent phenomenon. It brings up pebbles and rocks and disturbs the beaches. And you can detect some of those. But in particular, for the particular case of the Pacific Northwest, around 1700, actually in 1700, a tsunami was generated. It was recorded in Japan. And by looking at the tsunami records in Japan, both the historical record and the actual geologic record of the tsunami, modelers have been able to kind of back project that, go backwards across the Pacific, show that the source of that tsunami was in fact the Pacific Northwest, and get a good date, 1700, for that event. That event looks like to be about a magnitude 9, 9.5. That's bigger than what we had in Chile just a few weeks ago. And it's about as big as the biggest earthquake we've recorded instrumentally. So now that we know that that boundary can support a monstrous earthquake, a magnitude 9, we can go about the job of measuring how fast the plates are converging, making some assumptions about how stress is building up, and come up with some sense of what the repeat interval might be for that earthquake. And sad to say, we're pretty close to the repeat interval for that earthquake. So that's a forecast. It's not a prediction, it's a forecast. And thankfully, at least in the United States, going back a decade or more, Seattle and Oregon have been well aware of the potential for that earthquake, and they're taking the appropriate steps, one would say, to try to mitigate the potential damage. We do talk about things like the big one, when it'll occur, how big it will be, what the impact will be. A curious thing, by the way, is that we're getting better at predicting the impact of an earthquake than we are at actually predicting an earthquake. Once we know once we have a scenario earthquake, for example, of a certain size, a certain location, our computer modeling really is very good. So we can actually, with a computer, generate the possible ground motion from a scenario earthquake. We know how buildings interact with the ground and what will cause a building to fall down. We even have reasonable estimates of the casualties that might arise and the economic damage as well. So we're getting very good at predicting the damage. And we've constructed such a scenario for California. And the reason for that is that over the next few decades, 30 to 50 years, the chance of having a major earthquake in California is pretty close to 1, pretty close to unity. In some sense, it's really safe for a seismologist to say that because earthquakes happen. Almost certainly a large earthquake is going to happen in California. So I'm not sticking my neck out by saying there's a good chance of an earthquake happening. But the question is where it'll be and how big it will be. And that we base on trenching. We base it on very fine measurements of the crust moving. We have better calibrated models of the faults and the frictions on the faults. And so we're coming up with sort of a community understanding of what the big one might be. The U.S. Geological Survey, an academic consortium called the Southern California Earthquake Center, which actually involves seismologists from all over the U.S., if not the globe, have come together with a consensus statement, a California rupture forecast, as it were. And the two areas that are potentially very dangerous are a repeat of a major earthquake along the southern San Andreas, east of Los Angeles, but still close enough to do considerable damage to Los Angeles, and of course in the Inland Empire, east, basically along I-10 and going down toward Palm Springs, there's a good chance of significant damage and significant casualties there. The second area is up in the East Bay, not a repeat of the 1906 earthquake, which was on the San Francisco Peninsula, but in the East Bay along something called the Hayward Fault, really part of the San Andreas system, but a separate fault. That's the fault that colloquially you may remember sort of runs right through the Berkeley football stadium, the hills above Berkeley, and so on. So, Cal might have difficulty fielding a football team if that earthquake occurs, but our predictions of damage there are pretty severe as well. But again, knowledge of what might happen, and particularly the damage that might happen, goes a great way to providing the political will and, in fact, the funding to do something about it. Can't stop it. Can't stop an earthquake. But you can build strong buildings. You can prepare the population. You can make people aware of what they might do when they feel an earthquake. And there are other steps we can take as well. We can predict. We're getting better at forecasting. But there's also something interesting called earthquake early warning systems. And this is something that has taken a while to develop, but when you think about it, it's kind of obvious. And let me start with the following analogy. Earthquake waves, an earthquake occurs, it generates ground motion. That ground motion leaves the earthquake zone, the rupture zone, in a series of waves. And there are several types of waves, and they all move at different speeds. Some of our students learned that these are primary, secondary, surface waves, and so on. And the primary waves are very fast, the secondary waves are slower, and the surface waves are slower still. What's interesting about that progression is that the primary waves, though fast, aren't very large. The secondary waves are slower but larger, and the surface waves, slower still, are larger still. And so it's the large waves that do most of the damage. So the theory is that if you could detect that little bit of a P wave coming along, it's not going to do a lot of damage, but it might give you enough time, ranging from a few seconds, a few tens of seconds, to maybe even close to a minute or so or more. It might give you enough time to do the sort of things that would save people, save structures. You could stop trains, you could shut off gas, you could get people to find safe haven inside the buildings, for example. If you could do that, that would constitute a pretty decent early warning system. And so there are experiments on trying to do that. It's been implemented in Japan, it's been implemented in Taiwan, and there are other countries around trying to investigate these systems. You know, preparing for an earthquake is multifaceted, multidimensional. And the first thing really is being aware. Yes, I've said that earthquakes can occur anywhere, but they're more likely some places than others. So, you know, basic awareness of where your house, where you work, where you are relative to the faults that might cause an earthquake. That's a matter of public education. But once you know what your risk might be, you have to make some sort of personal judgment, or if you're a government, some sort of social judgment about the level of risk that you're willing to accept is going to be. And if you're willing to accept, or only willing to accept, a low level of risk, then there are a number of things you need to do. You need to ensure that major infrastructure is resilient, that our water lines, our power lines are built in such a way so that they won't break, that bridges and highways won't fall down, that fire stations will remain standing so that the fire personnel can respond, and that hospitals remain standing. With respect to individuals in their homes, if you're in an earthquake zone, ensuring that your building is up to code, if a code exists, ensuring that you follow that code, and even little things like keeping the knickknacks away from the edge of the shelf, keeping your dishes way back. Those are the sorts of things that can make the difference between sort of ho-hum, boy, was that an interesting event, to something that was a disaster. And these are all written down. You can go to the FEMA websites, USGS websites. There are a whole list of these things. The problem arises when, first, you don't have building codes, or those codes aren't enforced. That was the situation in Haiti, where you don't have the national or social wealth to actually consider this something you can do. I mean, I don't mean to bring up Haiti constantly, but the issue there was that there were so many sort of day-to-day problems facing Haiti culture and Haiti government that something that might happen really can't get on the radar screen. And you could argue the right or wrong of that, but that basically is the situation. And sad to say, that happens throughout the world. So, you know, the basic things are really quite easy to do if you've got the money to do them, and if you've got the public awareness to do them, and if you've got the political will to do them, if you're dealing with the commons, if you're dealing with infrastructure. Where you don't have the political will or the wealth, there are a number of things that the community is trying to do. There's a lot of concentration on building small-scale community awareness, so that the awareness of disaster, the awareness of potential disaster, I should say, occurs almost at the household level, and enabling people to make decisions, but also giving them sort of the simple things that they could do on a day-to-day basis. Not just for earthquakes, but for floods, for landslides, and for that matter, for longer-term issues like sea level rise and climate change. You know, one of the key things that we're doing at our institute and elsewhere is trying to bring the knowledge we have about Earth processes. You know, it's a dynamic planet. It's fun to look at. We enjoy doing that, but it affects people. And one of the things we're trying to do is to bring that knowledge, not just throw it over the fence so that policymakers can use it, because, you know, there's not enough feedback in that kind of a system. Scientists need to understand social and cultural constraints on using the information, and in fact, even the utility of the information that they provide. And, if I may say, I think the social scientists and governments and NGOs need to know what they don't know. And that's a difficult task. But to be honest, it's an interesting and important thing to do, and we're getting better at it. You know, Chile is a particularly interesting earthquake from a seismological point of view. First of all, of course, it's very large, a magnitude 8.8. That's what we would call a great earthquake, where we use great in terms of the wow factor, if you will. It did kill 700 people or thereabouts. It caused billions, tens of billions of dollars worth of damage, so the economic impact on Chile is going to be severe. But we don't get a magnitude 8.8 very often. The only reason, by the way, there weren't more casualties in Chile and more damage in Chile is that the earthquake was off the coast. It was in the subduction zone. It generated tsunami, as we saw, but it wasn't a direct hit. But being anywhere close to an 8.8 is enough of a hit to be dangerous, and that's what happened in Chile. But it was the result of a subduction zone. It's part of what seismologists call the circum-Pacific seismic belt or earthquake belt. It's what's colloquially known as the Pacific Ring of Fire. That's actually a great name because indeed the Pacific is ringed by these subduction zones. When a subduction zone means that the heavier, denser crust of the Pacific Ocean basin is essentially diving under the lighter, less dense crust of the continents surrounding. And as it dives underneath it, it sticks and slips and causes earthquakes. Roughly 70 or 80% of the world's biggest earthquakes occur in the Pacific Ring of Fire. It's a gigantic source of tectonic energy, of earthquake energy. The other interesting thing about that, by the way, and the reason it's called the Ring of Fire is because as these plates dive down underneath the lighter continent, pieces of them melt, and that melt becomes magma that just drives up through what we call the mantle and the crust and creates volcanoes. So it's kind of part of an ecological recycling mechanism going on. You're taking old crust, throwing it out, sending it down the subduction zone, recycling it into new material, just like you throw a paper bag into the garbage or in the recycling bin. So that's the basics of the tectonic activity. These earthquakes tend to be very large because these are large plates. The continents present a significant barrier to subduction in many cases, and it takes a long time for stress to build up. One interesting thing is that we knew about this problem in Chile, of course, for a long time, and of course the Chileans, who have an extraordinarily advanced and professional capacity to deal with earthquakes, knew about this as well. But 20 or 30 years ago, using very simple components of the plate tectonic theory, this particular area was identified as a so-called seismic gap, a place where an earthquake was basically overdue. Couldn't predict it, but we could forecast it, and that's what, in some sense, saved Chile. Large earthquakes do strange things. Of course, what an earthquake does is, in addition to breaking the ground, it actually moves big crustal blocks around. And when it does that, it shifts the distribution of mass of the Earth. Now, because this wasn't an asteroid or a comet hitting the Earth and causing all these vibrations, the Earth has to conserve its angular momentum. And the way the Earth conserves its angular momentum when crustal blocks shift like that is to change the rate of rotation and to slightly shift the axis of rotation. It can be calculated, but it really isn't measurable. On the other hand, if you're being paid by the microsecond, maybe it's something that you might worry about. But the interesting thing is that we can calculate it, not that it is, in fact, something we ought to worry about. Now, Haiti is a different kind of an animal, but it pays to think about what's really happening around South America. The Chilean event, a subduction event, was a subduction of a piece of the Pacific plate, in this case called the Nazca plate, but a smaller plate going underneath Chile, underneath the Pacific Ring of Fire. And so this is a case where the continent and the Pacific Ocean are converging against each other, and the Pacific diving down because it's denser. But if you look at the northern and southern parts of South America, picture it in your mind, you've got the Caribbean to the north, of course, and you've got the Scotia Sea to the south between South America and Antarctica. And those are two very interesting plates. In some sense, you can think about those plates as resulting from the squirt of material in geologic time going around South America. So if you can't subduct this stuff, if you can't get everything underneath South America through subduction, that stuff has to go someplace, and it goes north and south and sort of squirts around. And the Caribbean plate is one of these plates that got squirted through the gap between North and South America. Of course, it's a vast simplification, but it's actually the way we teach it. It's kind of a fun thing to think about. And so the Caribbean is actually itself a small plate. It is a significant part of plate tectonics. It was well recognized as a plate, but it's basically squirting past South America between North and South America, going from west to east. And it's moving at a little less than an inch a year relative to North America. Now, the unfortunate thing for Haiti is that for geologic reasons, Haiti lies along that northern boundary. And because this is a squirt boundary going from west to east, that is what we call a strike-slip fault. It's a fault that moves sideways. There are some complexities to that, but that fault was also recognized as being capable of supporting a magnitude 7 or greater earthquake, actually a 7.2. In fact, that forecast was made in the professional literature in 2008, 2 years ago. And we've known for about 20 years that that fault was dangerous. Anyway, that wasn't a subduction earthquake. That was a sliding earthquake. And sliding earthquakes, or strike-slip earthquakes, are dangerous also for a number of reasons. First of all, they tend not to be as large as a subduction earthquake, but they can be large enough. They also, in this particular case, they occurred on land, and unfortunately, it was almost a direct hit on Port-au-Prince. The earthquake itself was shallow, which increases the amount of vibration that people on the surface feel, and was very close to major population centers. So, if you will, it was sort of the perfect storm of bad effect. Even if Chile had good building codes and good construction, I think we would have seen tens of thousands of casualties anyway. Very difficult to deal with an earthquake of that sort. But it was a different kind of an animal. We've looked at the Chile earthquake in many ways, and we're continuing to do so. In fact, there are a number of conferences coming up in the next few days to try to move to the next phase of Chile rebuilding and sort of essentially make the rebuilding of Chile more risk conscious, not just for earthquakes, but for the storms coming up and the annual storm season, the annual hurricane season, and concomitant landslides and other natural hazards. But trying to understand these earthquakes on land, these strike-slip earthquakes, is a very complex problem. And one of the things that we're very worried about in Haiti is that this earthquake may have stressed parts of the fault that did not rupture on January 12th. When an earthquake happens, it doesn't zip open the whole fault. It only zips open, in this case, about a 40-kilometer segment of it. And there's still stuff on either side that did not rupture. Well, that stuff may have been overstressed. That piece of the fault may have been overstressed. And so the potential for an earthquake on those segments may actually have increased. That, again, is a computer model. It's something that we're working on. It is hard to predict, but it is something that, as a forecast, ought to play into the way Haiti is being rebuilt. Chile, we could do the same thing, but to be honest, Chile, apart from the economic damage and the economic recovery, Chile has a good capacity to deal with future earthquakes and the outcomes of this earthquake. With Haiti, I hope that the international community will work with the Haitians to build that capacity so that they can monitor the potential for these future earthquakes. Well, obviously the public has a great interest when an earthquake happens, and so we do our best we can. The questions tend to be repetitive. Almost always we get a question from somebody about whether they can come see the Richter scale. Do we have an example of the Richter scale? The Richter scale is a mathematical calculation. In fact, seismologists don't use it anymore. The only reason we give a Richter magnitude, frankly, is for the press and the media, but we have much better ways of measuring the energy of an earthquake now. But the second question that's cropped up, and it's fascinating in its own right, is that the first time I heard it, I thought it was a fluke, but I've heard it so many times since Haiti that I wonder what's going on, and that is, are these earthquakes related to global warming? I'm serious about that. I'd say that most of the press and most of the public that have called in, that that didn't have specific domain knowledge has asked us that question. We also get questions whether 2012 is coming a couple of years early. We get that sort of thing. It's just the end of days. But I think it speaks to something more interesting, which is that earthquakes and major disasters have a certain impact on the public consciousness. And I think earthquakes more so, or even volcanic eruptions more so than anything else. We get a major hurricane, a few major hurricanes every year. We get floods every year. There are major disasters that cause an enormous amount of economic damage and casualties. But yet, we hear about them relatively often, and so we kind of think of that as kind of background. This is what the Earth is doing to us. But earthquakes, especially major ones, are relatively rare. We get a few major ones a decade, particularly ones with huge numbers of casualties. And the concept of an earthquake, that it shakes the firmament, that it removes your footing, that it could destroy everything in a blink of an eye, and that it is unpredictable, that it just happens. Even if you're rational in a scientific way, even if you're rational in even a theological sort of way, it has to have some impact. The scientific response to the Chile earthquake, although modulated a bit by the damage and by the casualties, still was, this is a major earthquake. We've got to look at this as well as we can because we only get a couple of shots a decade to look at this. So now there are teams of scientists and lots of instrumentation going to Chile. But when you get down to Haiti, or something like Haiti, when you get a direct hit on a capital city, when the bulk of the nation is affected, where you have damage that far exceeds their economic ability to come back, coupled with the fact that an earthquake literally moves the ground on which you're sited, you start asking basic questions like, should I even be here? Should I be living here? Do I have to move? What is the future of my country? What is the future of my city? And those are the sorts of questions that I think have such a big impact on the public that by necessity, I think we've got to talk about them. We've got to talk about what it means. I think science is somewhat ill-equipped to do that. We quantify everything. We enumerate the energies, the displacements, the ground motion. We have technology, and we have lingo. But none of this relates to somebody who's asking the question, my house was destroyed, where should I move? And it relates, of course, in a very quantitative, scientific way, but how do you approach that person? How do you assure them that the situation has a rational response? And I don't think we have a good way to deal with that. So a lot of the questions we were getting and a lot of the thinking that generated had to do with these central questions of what does this mean, and particularly for the future of Haiti, but what does this mean when we talk about taking steps to mitigate against future tragedy, future disasters, not just for earthquakes, but for the other major natural disasters as well. And to me, that, and to many of us, I should say, it's not that we haven't thought about this before, but it seems to me to be an area not just of research, but of sort of a way to link directly to the public, directly to the people who need to understand what it is we're doing as scientists. I could make the same sort of argument about climate change, for example, but earthquakes serve, I use a phrase, and I don't mean to use it lightly, but earthquakes serve as training days for the major environmental disasters, major environmental stresses that our planet faces. And if we can begin to address how we relate to the public, how we provide assurance, how we help the public to understand what it is that's happening to them, if we can understand how to do that for major earthquakes or major hurricanes, then perhaps we can do something about stuff that's even more major, more in the future, more emergent, more probabilistic. where we actually might have a chance in modifying our behavior to do something about it. So what I've taken away from this interaction from Haiti and Chile, and I must admit it's not new to this earthquake. We've had it before with the Indonesian earthquake and the Indian Ocean tsunami. We've seen it in earthquakes going as far back as the 80s and the 70s in places like Armenia and China and so on. But what we've taken away from this is that there's a conversation that scientists have to have with the public that the public will regard as deeply meaningful, which means we can't just throw our results over the fence. We can't just stick with our technical journals. There's got to be some other mechanism. And in my view, I think universities where we ascribe to liberal thinking, the small L liberal, that ought to be a good place to do it. And I think the universities have that kind of a role to play beyond the roles that governments and other social institutions play. Yeah, it's the rare seismologist who hasn't experienced an earthquake. We call them theoreticians, by the way. Yeah, I've experienced earthquakes, nothing larger than about a magnitude 6. And of course, I've been in aftershock zones where magnitude 4s and 5s are fairly frequent. And you take steps to deal with it. But it's very difficult for me to imagine what it would be like at an 8.8. I mean, or even a 7.0 that was a direct hit. I personally feel fortunate that I haven't been in that. And I sometimes joke with my colleagues, that's why I work in New York and not in California. But on the other hand, we understand earthquakes in the abstract. And the visceral feel of an earthquake is something that perhaps might contribute to the conversation we need to have with the public. And maybe there ought to be a program to get a lot of seismologists into earthquake zones so that they can understand what it's like. I'm only half facetious there. But to experience an earthquake is to know what it means to somebody who may not be a seismologist, who has a house that's just been destroyed, who has a livelihood that has disappeared, and who has a government that's in shambles. And maybe all we can do is extrapolate, but I think it's something necessary to think about.